Hello, everyone. Nice to see you guys.
Good afternoon.
Hi.
Good afternoon.
Good afternoon.
Good afternoon.
Hello.
Good morning.
Hello. Hello.
Hello.
Hi. Okay, guys. And I guess some people may join a bit later. So first of all, what I would like to mention that your long Kappa accounts should be already prepared. So you should be technically capable of log in into long Kappa. And also the test homework assignment for this week should be also assigned. So you should receive some messages, I believe, with this information. But from my side, I also need to recall you about this, so you can go try to log in long Kappa and practice with solving problems there and submitting your solutions. So again, please be very careful with the format. Now it doesn't matter for this week. It doesn't count for your final grade. So it's just made for your convenience in starting like the initial stage of your work with long Kappa. But starting from the next week, week number 3, you will already have homework which will be evaluated. So please be very serious about this and follow the required formats for submitting your answers. Again, another reminder, it doesn't matter for this week since it's test week and nothing is evaluated. But later, if you are for sure convinced that there is some problem with the some issue with the long Kappa problem, then the steps what you do in order to appeal for this, you make screenshot of your problem, screenshot of your answer submitted in the long Kappa, and a copy of step-by-step clearly written solution, like your solution of this problem. So this information should be provided attached to your appeal, otherwise it will not be considered. So all appeals with such full package of information we will take into consideration during our meetings of instructors and address all these issues if they exist. But please don't be in hurry to appeal. First, just double and triple check if your solution indeed is the right one. Okay, so any questions with this? Did someone have a chance to log in already in long Kappa? Any experience? Can you share?
I have a question.
Yeah, sure.
Hello. Where do I get like my user logins like to long Kappa?
Okay, you see that someone already answered in the chat that yes, they logged in. I believe you should have get it. Yeah, there are more response. I think you should get it a message to your email, like university email. If you didn't get it, try maybe your university ID, which you and UID. That may be how it works. But if it doesn't work and you didn't get any message, then you can contact our long Kappa administrator, Azamat. I shared his email with you guys during first lecture, and also his contacts can be found in the course manual. So please go look there, and you can contact him. So that's okay. Don't be stressed out, because we have whole week for practicing and testing things. So you can contact him, and this issue will be addressed. But maybe probably you can also ask other students if you have, like, for instance, some chat or something like that, and maybe they can provide you some information how it worked for them. Okay, so yeah,
Это
there
меня
are
зовут или чё?
guys who is not involved in the discussion, please switch off your microphone. That is the request. We cannot make background noise for 100 people. Okay, so with this is clear, and you see that people write in the chat that not even without getting emails, like notifications, that they are already involved in Long Kappa, they still can log in. So from my side, I downloaded the latest list of students in my two sections, section 3 and section 4, and send them to Azamat. I don't see any reasons why some of you should not still have access to Long Kappa. If that is the case, probably there is some technical problem, like problem, which definitely can be addressed by help of Azamat. Yeah, sure. Thanks for comment. I agree that I can switch off someone's microphone, but the problem is that I don't see the person who is making noise. There are 95 people now involved, and I see only few wishes, like changing randomly, and then it's difficult to identify. So please don't create some additional problems for all of us, and take care that your microphones are muted unless you want to ask a question. Good. So I guess this question is discussed, and you're welcome to start trying to log in and check how it works. If not, again, contact Azamat, because this should be resolved by the beginning of next week, so you have full time for working on your first graded homework assignment during week number 3. Okay, so another question. Work during the first week. No, for this homework which is assigned for this week number 2 will not be graded. It's just for practice. So that is made to allow you practice with Long Kappa and understand how it works. So don't worry with this homework. You can submit it. You may not submit all answers. It's up to you. So just be sure that you understand how it works and what is the requirement for submitting the answers.
I'm sorry, can I ask real quick?
Yes, sure.
So this is about weekly assignments. From now on in the future, from the next week, are they all going to be till for like whole week?
So
like the deadline will be on Sunday.
Yes, yeah, it will be like this until the end of our semester. Every week, at the beginning of the week, you will get the assignment. You will have whole week to work on this assignment, and the deadline for submission in Lonkapa is like Sunday evening, I believe. And be sure you manage to meet the deadlines, because again, Lonkapa will not accept your answers after the deadline, so you will lose points.
Answers are checked instantly or not? Because for some problems we have multiple attempts, and I don't understand how it works. Like when I submit one answer and then it says this is incorrect, and I have another attempt, or how?
I mean, if it is incorrect in terms of something is missing, for instance, you forgot to put units, or you used not enough significant numbers, then it claims that it's not accepted format, and you can submit your answer again. However, if it's already accepted and is wrong, then most likely you will see this immediately, or at the end of the week. So still probably at the end of the week, you will see the results of your previous homework. So you submit the answers by the end, like by the deadline, and after deadline, these results should be apparent. But there is a chance that you may see it immediately. That's a good question. I need to double check this. Also, yeah, I can ask Azamat. He definitely knows better how this algorithm works. When okay. Any more questions? So, yes, okay, cool. So recalling our previous lecture, we discussed the main basics of vectors. We gave the definition of vector and discussed basic operations which can be done with vectors, like adding vectors, subtracting, introduce unit vector, which is very useful concept for working with vectors numeric, quantitatively, and also discussed two types of vector products: dot product and cross product. So now we continue further. Actually, we start discussing the kinematics. And our first topic, which will be covered during this lecture, is motion along a straight line. So this is a specific case of motion when we do not operate with vectors yet, because when bodies move along the straight line, we set some origin of coordinates, and the sign of displacement shows us in which direction, back and forth or left or right, this body moves. There are no other options. It cannot go in other dimension, because this is by definition motion in along a straight line. So in this case, the direction is defined by the sign, and speed and velocity are technically the same quantities just with if speed you provide with just numerical number, velocity in this case is specified with the same numerical number, but in addition you need to clarify what is the sign, which tells in which direction this motion is happening. Okay, so let us maybe change the camera. And let's start from this motion along a straight line. So we have axis x along this straight line, then have some body at in initial position, its initial position at the origin of the axis x, so x is equal 0. So if it moves along axis x, then displacement can be defined by this position x1, like coordinate of this body after motion. And this, in this case, for this axis orientation, x1 will be positive. So this displacement is positive because it happens in the same direction as the orientation of the axis. Then if we have motion in the opposite direction, let's say here is x2, we have negative displacement. X2 is smaller than 0 because it goes in the direction opposite to the orientation of the axis. Let's say if we have axis x and our body is located at some randomly chosen point, let's say x1, then it moves to the right. And here we have point x2. Then displacement will be defined as x2 minus x1, and this will be larger than 0 because this motion happened in the direction of the axis. The main question which kinematic is answering. Can someone help me to state this question and highlight it? What is the most important task of kinematics?
Calculating object movements and displacement.
Yeah, that is true. So we, first of all, we don't care about the reasons of the motion. That is question of the dynamics. Here we kind of calculate the motion of the body. In other words, with a set of given initial parameters, which is initial position, initial speed, and initial acceleration, we should be able, based on kinematic equations, predict where the body will be in some time interval based on these given initial parameters. So now let us try to come and to this point when we can introduce equations which actually can be useful in order to answer this question and say, okay, let's say with these known parameters, after some time interval, we will definitely know where this body will be located. So let's say we have displacement x as a function of time. So keep in mind, these are not two-dimensional motion. So it's motion along straight line along axis X. And here this horizontal axis is time. And we have, let's say, such dependence. So means that starting from this, let's say, point A, initially for some time interval up to here, this body was moving along axis X, the displacement was positive. Then it is moving like backwards and then again forward. Let us consider some element of this curve. And here we have T1 and T2. So we consider some time interval between T2 and T1. So this is delta T, is change of time. And this is delta X, is change of body's position along axis X during this interval T2 minus T1. So we want to know the position as a function of time. So this is the main question we ask. That is necessary to answer at any time. We want to know where our body will be. In order to do so, we need to introduce certain physical parameters which can describe motion. So of course we have some initial position x naught that is like geometrically defined where exactly this body was located at the time t is equal to 0. However, we need two other physical parameters in order to describe such motion and get this function of position of this body as a function of time. So first of all, we can introduce average velocity. Average velocity is defined as x2 minus x1 divided by t2 minus t1. So in other words, it's this triangular here. We have delta t, delta x. So it will be delta x over delta t. And this is equal to tangent alpha. And alpha is this angle. So this is average velocity, means body not necessarily moves always with this velocity, but on average, during this time interval, we get this velocity. It can change. And in order to be more specific in describing the motion of this body, we definitely want to go to instantaneous, so-called instantaneous velocity, means velocity at every given moment of time. That is more useful information because it provides more options to finally derive this equation x as a function of time. So how do we come to instantaneous velocity? We will just call it v, lowercase v. And it is defined as limit of delta t approaching to 0 of this ratio delta x of delta t. So How do we call this formula when we have limit of delta t goes to 0, which is in the denominator of some ratio delta x over delta t? I believe that you guys should be familiar with basics of calculus from your school program. And if by any cases you don't have understanding what is derivative and like limits, derivative, differentials, and integrals, please pay attention to these topics. You don't need to be big experts in calculus, obviously. You will study it during the mathematics course at university. However, basic understanding of these topics is mandatory. So this will be the derivative of our function, unknown function at this point, dx over dt. The first derivative of position over time. So this is the definition of instantaneous velocity. How does it work? If we have this limit delta t approaches to 0, then this point t2 approaches to point t1. Obviously, for during such short time interval, when t1 and t2 are located very close to each other, at negligibly small time difference, this points which describe position of our body, it's x1 and x2, also will approach to each other. And then we will deal with very short portion of this curve, where we will be able to define this tangent alpha at each given point, means at each given time moment. So this is technically the definition of derivative. It gives us the tangent of the curve at each point of the independent variable. Here, independent variable is time. And since we have dependent variable position, independent time, derivative gives us instantaneous velocity. However, it is not enough. We need to introduce one more physical parameter in order to be able to describe motion of a body and get this function x as a versus time. Another parameter which we have to take into consideration is acceleration. So first we deal with average acceleration, and that is delta v over delta t. So technically, acceleration is the speed of changing the velocity, how fast velocity changes over time. And of course, it will have impact on our position over time if our body accelerates, for instance, or in the contrary, it slows down. So this is average acceleration, but it is some average value along relatively long time interval. That is sufficient, maybe enough for certain tasks, but in order to get the complete form for this x versus t function, we need, of course, instantaneous acceleration, which is acceleration at any given time moment. So the definition of this instantaneous acceleration is limit delta t approaches 0 of delta v over delta t. This is equal to the derivative of velocity over time, or since we know that velocity itself is derivative of displacement over time, it will be second derivative of displacement over time. So it will be d squared x over dt squared. So this is how we define our key physical parameters, which are used to explain motion. Actually, in this particular case, along a straight line, but similar concepts are also applicable for multidimensional cases, which we will consider quite soon when we deal with motion in 2 dimensions. But these definitely concepts of definition, average instantaneous velocity and acceleration, should be very clear to every one of you, because these are basement of mechanics.
Excuse me, may I ask a question?
Yes, sure.
Right now, we're only defining how we got the final formulas, right? We won't need to use the limits every time we calculate, right?
No. Now we give definition of the concept of these parameters, and that's why we show every step. But later we will deal with some functions, and if it's necessary, we will take derivative, but we will not write this limit delta t goes to 0
We'll only use the final formulas, right?
yeah, sure, but we are on the way to derive these final formulas, which we are going to do right now. So we will final formulas for the case which is in the scope of this motion along the straight line. So one of the very classical example which we will consider is motion along a straight line with constant acceleration. So the best example, and quite common what we observe in everyday life, is just free falling of a body. It falls with constant acceleration along like g along straight line. But that could be technically any motion, you can organize it. But the key requirements here, which we're going to consider, and I would like also to highlight that always when you deal with some derivations, you should be very careful in defining initial conditions of your model within the frame of which you will derive the equations, because you need to be very clearly aware of limits of your model and those conditions where this model can be applied. So in our case, we consider motion along a straight line, let's say along axis x. Here is our body, which moves with some initial velocity. Initially, it is located at some initial position x naught. Initial velocity is v naught, and some acceleration, which is larger than unity, and it is constant. So now we want to get the general equation which describes the position of our body at any given moment of time along this axis x. So we know from the previous discussion, from the definition of velocity and acceleration, that velocity is first derivative dx over dt, and acceleration, instantaneous acceleration, is second derivative or first derivative of velocity. So now we need, what do we know? We will go from the end to the beginning now, from known parameter, and then we will proceed further in determining unknown parameters. So we know that acceleration is constant, means that instantaneous acceleration doesn't change. It is constant value at any given moment of time. That means that we can, by integrating this equation, A acceleration is equal to first derivative of velocity, get the velocity of this body. So let us do it.
Sorry, isn't it like acceleration derivative time squared? Or
Yeah, d square. Yeah, thank you. So now let us do the integration. So no, not A. Maybe let's write it here. So A is equal to dv over dt. From here we can write that dv is equal to A times dt. And now we integrate left and right sides. So from the left, we will have integral dv equal to integral A times dt. So this will be just v, this integral. And here we have this A. A is constant. We know this. So we just take it out from the integral. We have A times integral dt. And finally, we get that it is equal to A times t and plus some constant. Because when we have not defined integral, we always get the answer with the accuracy of some additional constant to this equation, which we get at the end. So what, in order to have the full equation which describes velocity as a function of time at any point of time, we need to define this constant c. And this constant c is our initial velocity. So that's why we can write that v, velocity, at any given moment of time will be equal to initial velocity plus here, because our acceleration is positive, we remember this, acceleration times t. So this is first step. We define one of the key parameters which we require to know where our body will be located. So v is equal to v naught, initial velocity, plus acceleration multiplied time. Since acceleration is constant, it will continuously, with the same rate, add up to the velocity over time. Now let us go to the second parameter which we need. and like second step which we need to do in order to get to this point when we finally derive equation which describes position as a function of time. So now we have this velocity is equal v naught plus a times t. We also remember that velocity is equal to the first derivative of position, like this displacement dx over dt. So from here we also can write that dx is equal to v times dt and integrated left and right side. So here we have integral dx, which is equal to x is equal to integral v times dt. Now, instead of v, we can put its expression, which is defined by initial velocity and a constant acceleration. So let us do it. Here will be integral v naught plus a times t times dt. And according to rules of integrals, the integral of a sum is equal to the sum of integrals. So we can write integral of v naught, it is a constant. So if we open this parenthesis, v naught is a constant, just initial velocity, times integral over dt plus a acceleration is also constant, doesn't change with time, so we can take it out from the integral sign. T squared times dt. So we have these two integrals, and we need to solve them. So first integral, we have v naught times t. Second one, it is plus a. Oh, sorry. Here is a mistake. It's not t squared, it's just t. T squared comes later. Integral t times dt. It comes from here. We multiply at times dt. So we have under our integral t times dt. So it will be a times t squared divided by 2. So this is according to table of integrals. It's one of the most fundamental rule of integration. Such integrals are given in this table of most common integrals, and I strongly recommend you maybe to print this table of integrals most common, so you have it next to you and can double check how different most common functions can be integrated. So it will definitely help you a lot with like during this course. Again, here we have some constant C2, because we always, after this not defined integral, we get some unknown constant, which should come from the boundary conditions, so-called. And in our case, boundary conditions tells us that since we are dealing already with position, like total displacement as a function of time. So this should be our initial position of the body. And eventually we can write the final equation, which is x. Maybe we can even specify here that x as a function of time is equal to x naught the initial position of the body plus v naught times t initial velocity times t plus at squared divided by 2. So by the way, if you remember during the first lecture, like actually was technically second lecture, when we discussed dimensional analysis, we also had some example for finding the relationship between position as a function of time when there is some acceleration and time. So we got x proportional to a times t squared. Not so far from reality. So the accurate analytical solution gives us the same equation, but just with the constant divided. So this equation divided by 2 with a constant of 1/2. So this is one of the key and probably the most important equation in kinematics of body moving along a straight line with constant acceleration. So this definitely, please remember, write it down and remember. But again, what is important, you need to remember how we came to this point, because this sequence of simple steps which are required to derive this equation gives you clear understanding of where it comes from and why it is in this form and not in others. So this is very important, because over time you will forget many equations, but you can always come to this conclusion and to this equation based on understanding the steps which are required to derive it. So you just may forget the equation itself, but the understanding of the concept could be with you forever. So I think that we are running out of time for today. So 12:49. If you have any questions, you're welcome. So summarizing what we have done today, we introduced the concepts of velocity and instantaneous velocity and instantaneous acceleration, which are necessary for necessary parameters for describing position of body in any moment of time. And on an example of a body which is moving along a straight line with constant acceleration, derived this important kinematic equation, which gives us the relationship between position and time. Next step, we will proceed already during our next lecture. We will express time and substitute it, and we'll derive equation which gives the relationship between position and velocity. So there will be no time included, and also quite useful form of this kinematic equation, which can be quite helpful in solving specific problems where time is not specified, but specified initial and final velocity. Then it is requested to determine the position of the body. So we will also derive this and explain in details. If you have any questions, you're welcome. If not, you can also ask if something was not clear during our next lecture on Wednesday. Thank you very much for
Can
attention.
I ask, please?
Yes, sure.
Do we have some recordings of this lecture or presentation in Moodle?
Yes,
or-
of course. Yeah. So it is not in Moodle. There is a link in this welcome letter which I sent you. There is a link to where all these lectures, online lectures and discussions will be available for you any convenient time.
All right, thank you.
Mhm.
And I have a question as well.
Sure.
Yeah, I tried to log into LongCappa with all possible password and login combinations. So I should write to Azamat Rozbayev's email, yes?
So if it didn't work for you, yes, sure.
Okay, but generally all the people use a new ID for both login and password, yes?
Most likely, yes.
Okay, I just wrote to
Mhm.
him. Okay, thank you.
Yeah, you're welcome. No problems. But double check that you are in this section, that it's not somehow messed up with registrar. So it's your section. Maybe specify also when you write to Azamat that you are from section 3 and double check it and specify this.
Okay, thank you.
Because we have, I guess, 6 sections, and yeah, it can be quite difficult to keep an eye on everyone. Okay, thank you for your attention. Have a good evening. Or actually day, it's not evening yet. And good luck to see you. Hope to see you all on Wednesday.
Thank you. Goodbye.
Thank you.
Thank you. Goodbye.
Thank you.
Have a nice day.
Thank you.
Goodbye.
Goodbye.